Hello everyone, I'm Guo Cheng Wei. Today we'll learn about modulation and demodulation technologies in optical communication and the basic principles and knowledge of coherent communication. A complete optical communication process involves modulation of the original electrical signal at the transmit end and demodulation and restoration of the electrical signal at the receive end. For a coherent optical communication system, digital signal processing and coherent detection are involved. DSP processing aims to enhance system transmission performance. First, we need to understand the basic concepts of modulation technologies, such as phase, constellation diagram, and the most commonly used basic modulation technologies, such as ASK, FSK, PSK, and QAM. We know that the physical states of a light wave include amplitude and frequency. However, there is the third state, phase. The word phase has two meanings in physics. First, a specific phenomenon or state in a regular and recurring change. Second, the fraction of the wave cycle that has elapsed relative to the origin. It's often denoted by an angle, and therefore it is also called a phase angle. For example, the moon has different phases in different times of a month, such as the new moon, the first quarter of the moon, and the full moon. The state of the moon we see is a moon phase. The distance between the first quarter of the moon and the new moon is the phase. In communications, the word phase has different meanings as well. First, it may refer to the state of a specific point on the wave at a specific time. Second, it may refer to the position of a certain point on the wave at a specific time, reflecting the state of the wave at a specific time. The first meaning gives information about the state, while the second meaning gives information about the location. As shown in the following figure, as time passes, the amplitude of the wave goes from 0 to maximum, from maximum to 0, and then from 0 to negative maximum. This process is repeated continuously. We can get information about the state of the wave at a specific time, the increasing or decreasing amplitude of a certain point, and the current value. These are the concepts of phases in communication. But how do we get the phase information? Taking the sinusoidal wave in the following figure as an example, at a certain time, the point is at the peak if the phase angle is 90 degrees, at the valley if the phase angle is 270 degrees, and at the peak again if the phase angle is 450 degrees. The waves are cyclic, so we can use a rotation vector to represent the phase. For example, a sinusoidal wave with a frequency f can be understood as the projection on the imaginary axis of a rotation vector, whose rotation angle velocity omega equals 2 pi f. Now let's have a look at three special relationships between the phases of two signals. First, when the phase difference between two signals is 0, we say that they are in phase. The corresponding rotation vectors are always in the same direction. For example, cosine omega t and cosine omega t plus 2 pi are in phase. Second, when the phase difference between two signals is pi, we say that they are reverse phase and rotation vectors of each signal are in opposite directions. For example, cosine omega t and cosine omega t plus pi are reverse phase. Third, when the phase difference between two signals is pi over 2, we say that they are quadrature signals, and the rotation vectors of each signal are perpendicular to each other. For example, cosine omega t and sine omega t are quadrature signals. Next, let's talk about constellation diagrams, a concept that is commonly used in communications. In digital communications, digital signals are often represented on the complex plane to visually illustrate the relationships between signals. This complex plane is a constellation diagram. So how do we get a constellation diagram? As we know, the phases are directional. For the previous rotation vectors, the phases begin from the origin, and the length of the line from the origin to the endpoint of the vector is called the mode of the vector. Therefore, we can get all the information about the wave just from the endpoint of the vector, such as the amplitude of the wave, the current position of the mass point, and the phase of the wave. In digital communications, a constellation diagram is a distribution map of these endpoints that carry bit information. Using a constellation diagram, we can intuitively visualize a signal's characteristics and the relationship between signals. Besides the direction and the mode of the vectors, what other information can we get from a constellation diagram? Most directly, the amount of information and the capability to resist interference, which are also what we care about most. First, the more points a constellation diagram has, the more information bearers are available, and the larger the signal bit rates are. Second, the more points a constellation diagram has, the shorter the distances between different points, meaning that signals are more likely to interfere with each other. With more interference, the transmission distance is shortened accordingly. Now let's talk about how optical communications make use of these three states. The process of optical transmission is the process where signals are modulated and demodulated. Modulation is converting the baseband signals into transmission signals at the transmit end. Demodulation is the reverse process at the receive end. A baseband signal is the signal source, which is the original 0-1 electrical signal code stream. Generally speaking, signal transmission is transmitting a signal along with the broadcasting baseband signals. There are three basic modulation formats. The first is AM/ASK, which uses different amplitudes of a carrier to represent different digital symbols and to transmit a group of code streams. The second is FM/FSK, which uses carriers of different frequencies to represent different digital symbols and to transmit a group of code streams. In a WDM system, we use lights of different frequencies as transmission channels. Channel resources are more valuable for us, so we use different frequencies to divide wavelength channels, which is called frequency division multiplexing instead of FSK. The third is PM/PSK, which uses different phases of a carrier to represent different digital symbols and to transmit a group of code streams. In optical communications, the most commonly used modulation format is PSK. PSK signals can only be coherently demodulated. These are the three most basic modulation formats. The other modulation formats are modifications or combinations of these three formats. To improve channel capacity, there is another common modulation format in optical communications called quadrature amplitude modulation. It uses both the amplitude and phase for modulation and to transmit bit information. Specifically, two quadrature carriers of the same frequency are separately modulated. They are mixed together for transmission and separated upon reception. Then the data is extracted separately. In MQAM, M indicates the number of symbols supported by this modulation format. Now, we know that the most common modulation formats in a WDM system are ASK, PSK, and QAM. Common PSKs include binary phase shift keying and quadrature phase shift keying. Common QAMs include 16 QAM and 64 QAM. BPSK can be understood as modulating two reverse phase carriers. BPSK uses two phases to represent 0 and 1. That is, one BPSK symbol represents one bit. QPSK can be understood as modulating two quadrature carriers of the same frequency. QPSK uses four phases to represent 00, 01, 10, and 11. That is, each QPSK symbol represents two bits. Accordingly, 16 QAM modulates 16 quadrature carriers of the same frequency, and each symbol can represent 4 bits. 64 QAM modulates 64 quadrature carriers of the same frequency, and each symbol can represent 6 bits. Different modulation formats offer different transmission capacities. We can see from the constellation diagram that the information capacities of these modulation formats in the ascending order are BPSK, QPSK, 16 QAM, 64 QAM, and the interference resistance capabilities of these modulation formats in the descending order are BPSK, QPSK, 16 QAM, 64 QAM. Now let's have a review of what we have learned in this course. We talked about the concepts of phase and phase angle, as well as how to read a constellation diagram. We also learned about the principles and performance relationships of 4 major modulation formats: ASK, FSK, PSK, and QAM. In the next course, we will talk about the principles of coherent modulation and another modulation format that is used in 100G high-speed systems, polarization division multiplexing. That's all for today. How are you guys holding up?